Hello, I'm going to read from Exercise Physiology, book 9th edition, by Scott Powers and Howley. I'm going to be on page 77, estimation of fuel utilization during exercise. A non-invasive technique that is commonly used to estimate the percent contribution of carbohydrate or fat to energy metabolism during exercise is the ratio of carbon dioxide output, VCO2, to the volume of oxygen consumed, VO2. This VCO2/VO2 ratio is called the respiratory exchange ratio. During steady state conditions, the VCO2 divided by the VO2 ratio is often termed the respiratory quotient, RQ, as it is thought to reflect CO2 production and O2 consumption by the mitochondria of the active muscles. For simplicity, we refer to the VCO2-VO2 ratio as the respiratory exchange ratio, R. How can R be used to estimate whether fat or carbohydrate is being used as a fuel? The answer is related to the fact that fat and carbohydrate differ in the amount of oxygen used and CO2 produced during oxidation. When using R as a predictor of fuel, and R being the ratio, the VCO2-VO2 ratio, when using R as a predictor of fuel utilization during exercise, the role that protein contributes to ATP production during exercise is ignored. This is reasonable because protein generally plays a small role as a substance during physical activity. Therefore, the R during exercise is often termed as non-protein R. Let's consider the R for fat first. When fat is oxidized, O2 comes with carbon to form CO2 and joins with hydrogen to form water. The chemical relationship is as follows. I'm not reading that. For R to be used as an estimate of substrate utilization during exercise, the subject must have reached a steady state. This is important because only during steady state exercise are the VCO2 and VO2 reflective of oxygen uptake and carbon dioxide uptake production in the tissues. For example, if a person is hyperventilating, i.e. breathing too much for a particular metabolic rate, excessive CO2 loss from the body's CO2 stores could bias the ratio of VCO2 to VO2 and invalidate the use of the ratio to estimate which fuel is being consumed. Carbohydrate oxidation also results in a predictable ratio of the volume of oxygen consumed to the amount of CO2 produced. The oxidation of carbohydrate results in an R of 1.0. Fat oxidation requires more oxygen than carbohydrate oxidation because carbohydrate contains more oxygen than fat. There you go. The caloric equivalent of 1 liter of oxygen is approximately 4.7 kilocalories when fat alone is used, and approximately 5 kilocalories when carbohydrate alone are used. Consequently, about 6% more energy, ATP, per liter of oxygen is obtained when using carbohydrate compared to fat as the sole fuel for exercise. Dang! It is unlikely that either fat or carbohydrate would be the only substrate used during most types of submaximal exercise. Therefore, the exercise R would likely be somewhere between 1 and 0.70. Table 4.1 lists a range of R values, which is the VCO2 and the CO2 ratio, R values, and the percentage of fat or carbohydrate metabolism they represent. Note that non-protein R of 0.85 represents a condition wherein fat and carbohydrate contribute equally as energy substrates. Further, notice that the higher the R, the greater the role of carbohydrate as an energy source, and the lower the R, the greater the contribution of fats. Table 4.1 shows how the caloric equivalent of oxygen changes with a mixture of fuel used. We need to look at this. That'd be some cool graph. That's fine, I guess. Alright. We'll eventually get into that. Alright, we're moving on. Alright. In summary, the respiratory exchange ratio is the ratio of carbon dioxide produced to the oxygen consumed. For R to be used as an estimate of substrate utilization during exercise, the subject must have reached a steady state. This is important because only during steady state exercise are the VCO2 and the VO2 reflective of metabolic exchange of gases in tissues. The caloric equivalent for oxygen is 4.7 kilocalories per liter when fat alone is used, and 5.0 kilocalories per liter when carbohydrate alone is used, about a 6% difference. We'll hold off there and move on to factors governing fuel selection on page 78 in a second. But that was pretty much page 77. See ya.